In this lecture, we are going to look at the pumping lemma for context-free languages. The pumping lemma for context-free languages states that every context-free language L has the following pumping property, namely there exists a natural number m, such that every word from the language that has length at least m can be split in 5 parts, u, v, x, y, z, in such a way that this middle part consisting of v, x, y has length at most m, v and y together are non-empty, so either v is non-empty, y is non-empty, or both are non-empty. And if we pump v and y simultaneously, then we always stay in the language. So for every natural number I, the word u, v to the I, x, y to the I, z is in the language again. So now let's prove the pumping lemma holds for every context-free language. Let G be a context-free grammar for our language except for the empty word, and let's assume that G does not have lambda and unit productions. So we've already seen how we can transform every context-free grammar in such a way that we remove all lambda and unit productions and we obtain a grammar for the same language except for the empty word. Let's say that our grammar G has k variables. Now we define a natural number m, this refers to this m in our pumping lemma, as follows. We say m is 1 plus the maximum number of leaves of a derivation tree of depth at most k plus 2. So m is 1 plus the maximum number of leaves of a derivation tree that has depth at most k plus 2. Now we take any word w from our language, such that w has length at least m, and we consider a derivation tree for the word w. Now, if w has at least length m, then it follows that the derivation tree must have depth at least k plus 3 by the choice of m. So if our derivation tree has depth at least k plus 3, it follows that there must be a path in this tree of length at least k plus 2. And we consider the longest of these paths. Now we look at the longest path, which has length at least k plus 2. Then it follows that along this path there must be a repetition of variables. Because we have only k variables in our grammar, a path of length k plus 2 must contain k plus 2 variables. Now we look at the deepest repetition of a variable along this path. So we choose a variable a such that this occurrence of a is repeated and this occurrence of a is as deep as possible. So below this there's no repetition anymore. Now what do we know? We have such a derivation tree where there's a path with a repetition of variables, and this u, z, v, y, x are the words corresponding to the leaves in this subtrees of the derivation tree. So in other words, we have derivations in our grammar of the following form. We have a derivation from our starting variable s to u, a, z, to u, a, z. From a, we have a derivation to v, a, y. And from this a, we have a derivation to x. And now, given that we have these derivations, it's obvious that we have the following pumping property, namely, we can repeat this middle derivation as often as we want. So this is this derivation, we can drop this derivation entirely and we can go immediately from this a to x. Or we can repeat it once, this is this tree. We can also repeat it twice or 3 times or 4 times. And if we repeat it I times, we get I times v and I times y. U stays the same, z stays the same, v and y are pumped, and x stays the same. So from S, we get a derivation to a word of the form u, v to the I, x, y to the I, z for every natural number I. Now this is the main property of our pumping lemma, but there were also 2 other properties stated, namely that v, x and y together have at most length m. And this follows from the fact that we look at the deepest repetition of a variable along the path, and we have chosen m in such a way that it is the maximum number of leaves of a derivation tree of depth k plus 2 and this number plus 1 still. So what does this mean? That this subtree that we are looking here at has depth at most k plus 2. Because if it would be bigger, then we would have a derivation in a subtree below it of depth k plus 2, because we have only k variables. So since we look at the deepest repetition of a variable, it follows that the subtree has depth at most k plus 2, and that means that the number of leaves in the subtree is bounded by m. So v, x, y together can have at most length m. Moreover, v and y together must be non-empty. This follows from the fact that we have removed lambda and unit productions from our grammar. So the derivation from a to a, so this middle part here, the derivation from a to a, must generate something around the a. It cannot just generate an a again. Otherwise we would have lambda unit productions in the grammar. So v or y or both must be non-empty. We will use the pumping lemma in order to show that certain languages are not context-free. And when we do this, we show that these languages do not have the pumping property that is asserted by the pumping lemma. And here it's again not sufficient to show that the property does not hold for specific values of m or specific values of u, v, x, y, z. We have to show it in general for whatever these are. So this is the pumping lemma as a formula. It says that there exists some natural number m, but we don't know which. For all words of the language that have length at least m, so because of this for all quantifier, we actually can choose the word, but it must be parametric because it must be longer than m, and we don't know what m is. There exists u, v, x, y, z. We don't know which they are, but we know that they have certain properties. And it states that for all I, if we pump, the word is in the language again. So due to this for all quantifier, if we want to show that the pumping property does not hold, we can choose a specific I and show that it's not in the language. So again, if we want to contradict the pumping property, then we have to show that the negation of this formula is actually true, so that this formula does not hold. So we have to show that for all m, there exists some word. So this for all we cannot choose, but we can choose w. For all u, v, x, y, z, we cannot choose them. And there exists an I, we can choose the I. So intuitively, we can think of this as a game. We are given a language L, and we want to show that L is not context-free. So intuitively, this formula can be understood as follows, namely that our opponent picks the number m. We don't have control over m. But we are allowed to pick a word w, but we must make sure that it has length at least m. Now, our opponent has to move again, and the opponent picks these words U, V, X, Y, Z. We don't know what words the opponent picks, but the opponent has to make sure that they have the stated properties. And now it's our move again, and we have to pick some I that gives us a word that is not in the language L. And if we can find such an I, then we win. And if we can always win no matter what the opponent does, then we have shown that the pumping property does not hold and the language cannot be context-free. So let's use the pumping lemma in order to show that the language consisting of words a to the n, b to the n, c to the n for n greater or equal 0 is not context-free. For a contradiction, let's assume that this language was context-free. Then the pumping lemma tells us that there exists a natural number m, such that every word that has length at least m can be split into u, v, x, y, z, such that this middle part has at most length m, v, y are non-empty, and when we pump v and y, we stay in the language. Now, since this holds for every word from the language of at least length m, we are free to pick one if we want to show that this pumping property does not hold. So what word from the language should we pick? We have to make sure that it has at least length m, so the obvious choice is that we just take a to the m, b to the m, c to the m. Clearly has length m. So now the pumping lemma tells us that this word a to the m, b to the m, c to the m can be split in 5 parts, u, v, x, y, z, with the given properties. Now we don't know what u, v, x, y, z are, but due to these properties we can reason about them. We know that the middle part, v, x, y, has at most length m. So if v, x, y has at most length m, then where can this middle part lay? This middle part cannot stretch across bm. So it cannot be that this middle part contains a's as well as c's, because then it would have to have length longer than m. If it would contain at least one a and one c, then it also must contain all the b's, namely mb's. So this is impossible because this middle part only has length m. So this middle part can either only consist of a's and b's, or only b's, or b's and c's, or only c's. We can summarize this, we can shorten this into 2 cases, namely we can say it either consists of just a's and b's, possibly 0 of them, of one of them, or just b's and c's. So since this middle part has at most length m, we may conclude that v, y consists only of a's followed by b's, or only of b's followed by c's. And here we say that we have JA's and we have KB's, and here we have JB's and KC's. And J and K can be an arbitrary natural number. But we know something more, namely we know also that Vy must be non-empty, so we know that J plus K must be at least 1. So Vy just consists of A's and B's, or just of B's and C's, and we know that they must be non-empty. That means if we pump V and Y, let's say we pump twice, then we increase either the number of A's and B's, or we increase the number of B's and C's, but we never increase A, B, C's at the same time. So that means if we pump twice, the word no longer has the same number of A's, B's and C's. In the first case, we have increased either the number of A's or the number of B's, or both, but not the number of C's. In the second case, we have increased the number of B's or C's or both, but not the number of A's. So this word cannot contain the same number of A's, B's and C's, and thus it cannot be in the language L. So we have our contradiction because the pumping lemma states that this word would be in the language L, and as a consequence L cannot be context-free. Intuitively we can think of this as follows. The opponent has picked M, we have picked the word A to the M, B to the M, C to the M. The opponent has picked the split into U, V, X, Y, Z. We have reasoned about this split and we have picked a pumped word, so we have picked an I, such that we are no longer in the language. Now let's have a look at a positive example, namely the language A to the N, B to the N for n greater equals 0. This language is context-free, so it should have the pumping property. So for what natural number M does this language have the pumping property? If you think about it a bit, then you will come to the conclusion that M is equal to 2 is sufficient. So if we take any word that has length at least 2, so any word from the language that has length at least 2, then we can split this word as follows. So we take a word W of the form A to the N, B to the N, such that the length of W is at least 2. Then we can split it as follows, namely this word A to the N, B to the N can be split into U, V, X, Y, Z. We take as U, we take A to the N minus 1. So this is a prefix. We take all but one of the A's. V, we take the last A. The middle part X, we leave empty, we take lambda. For Y, we take the first B. And for Z, we take the remaining n minus 1 B's. Now, U, V, X, Y, Z together give us the word A to the N, B to the N. So we have split our word. Does this split satisfy the properties stated by the pumping lemma? So first of all, this middle part, Vxy, has indeed length at most m. If we take V, it's just an A, X is empty, Y is B, so this middle part is just AB, and this has length at most 2. Also, V and Y together are non-empty. AB are both non-empty in this case. Now we have to check what happens if we pump. Do we stay in the language? If we pump V and Y, so we take the word U, V to the I X, Y to the I Z, what do we get? We pump single A's and we pump single B's. So if we pump I times, then we get a word of the shape A to the N minus 1 plus I, B to the N minus 1 plus I. And this word is, of course, again in the language. So if we pump 0 times, I is 0, then we get A to the N minus 1, B to the N minus 1, which is in the language. If we pump twice, then we get A to the N plus 1, B to the N plus 1, again in the language. No matter what I we fill here, we have a word that starts with a number of A's followed by the same number of B's. And we are always in the language L. So the language L has the pumping property for M is equal to 2. And we can always split words longer than 2 in this way as shown here on the slide. Now let's have a look at this language. This is the language of palindromes over the alphabet AB. So we have words over the alphabet AB such that the word is equal to its own reverse. This language is context-free, so it should have the pumping property. The question is, for what natural number M does it have the pumping property? So in this case, let's pick M is equal to 3. So what do we then know about words from the language that have length at least 3? So the word is equal to its own mirror image. That means if we look at the middle of the word, if we mirror this word around the middle, it should stay the same. So every word from the language that has length at least 3 is of this form. Now this looks a bit scary, but it's actually quite easy to understand. The T here marks the middle of the word. If the length of the word is odd, then T is a letter A or B. So precisely the letter in the middle. If the length of the word is even, then the T in the middle is just the empty word. Next to the middle, on the left and the right of the middle, we must have the same letter, C, because our word is equal to its own reverse. So if we mirror around the middle, we must have the same letter left and right. So C is the letter that is left and right of the middle, and S is the prefix up to this letter, and then we have at the end of the word the reverse of S. So every word W from the language that has length at least 3 can be written in this form. We have some prefix S, then some letter C, then T being either a letter A, B or lambda, the letter C again, and then the reverse of S. So S is a word over AB, can be empty, C is a single letter, and T either is a letter or lambda, depending on whether the word has odd or even length. Now, since we know that the word has this shape, how should we split the word and what should we pump? I think the idea is clear that we want to pump these C's. If we pump these C's, then the word stays a palindrome. So we will split the word as follows. We will split W into U, V, X, Y, Z, where U is this prefix S, V is the letter C, X is T, Y is C, and Z is the reverse of S. Now let's check that the properties stated by the pumping lemma hold. This middle part consisting of Vxy has indeed at most length 3. If we take V, which is just a single letter C, together with X, which is either a single letter or lambda, and Y, then we get a word that has at most length 3. It has length 3 if the T is a single letter. It has length 2 if the T is lambda. Also, Vy together are clearly non-empty. They are both the letter C. And if we pump, we get the following. We pump with I, so we take a word U, V to the I, X, Y to the I, Z. Then we basically get our word W, but now these C's are pumped I times. So we get S, C to the I, T, C to the I, S reverse. And clearly this word is the same whether we read it from left to right or from right to left. It is again a palindrome, so we are in the language L. So this language has the pumping property for M is 3, and we can always split words of length at least 3 in this form. Now actually, this language also has the pumping property for M is 2. It's a tiny bit more difficult to establish this. The idea is that we have to distinguish when splitting whether our word has even or odd length. Roughly, the idea is that if the word has even length, then the T here is empty and we can just pump the C's as we have done. But then if the T is empty, this middle part will have only length 2. And if we have a word of odd length, then actually we don't need to pump the C's, then we can pump the T. That's the rough idea. So I leave this as an exercise to you to establish that this language also has the pumping property for M is 2. Let's do one more exercise using the pumping lemma to show that the language is not context-free. Here we have the language of square words. So all the words of the form WW, where W is a word over AB. And we have already intuitively argued that this language is not context-free, but now let's prove it using the pumping lemma. So for contradiction, assume that this language was context-free. Then, by the pumping lemma, there exists some natural number m, such that every word from the language that has length at least m can be split in a certain way, such that these properties hold. Now, since the pumping lemma asserts that this holds for every word having at least length m, we can contradict this pumping property by picking a particular word that does not have the property. So what word shall we pick from the language that no matter how we split, we can always find some I that we get out of the language? So one possible choice for our word from the language is the following. We can choose the word a to the m, b to the m, a to the m, b to the m. This word is of the form ww. If w is a to the m, b to the m, then ww is this word. This word also clearly has length at least m, so it's a possible candidate. Now, we don't know how the word is split, but we know the properties of how it is split. So let's use these properties in order to reason what u, v, x, y, z could be, and let's try to bring it to a contradiction. We know that the length of this middle part, vxy, is at most m. So this means again that this middle part vxy cannot span across b to the m. So it cannot contain a's from this part, b's and a's from this part. If it would contain a's from this part and a's from this part, it would also need to contain m b's, but this is not possible because the word has length at most m. So the conclusion is that this middle part vxy either falls in this prefix consisting of a to the m, b to the m, or it falls into this middle part a to the m, b to the m, a to the m, or it falls into the suffix a to the m, b to the m. So it's either among these two blocks, or among these two blocks. So we can conclude that vy is of the form a to the j, b to the k, so some a's followed by b's, or it's of the form b to the k, a to the j, so some b's followed by a's, for j and k greater or equal 0. So the main point here is that it cannot be of the form a's followed by b's followed by a's again, because then this middle part would have to be longer than m. Also we know that vy together are non-empty, so we know that j and k together must be greater or equal than 1. So now what happens if we pump? If we pump, then we increase the number of a's or the number of b's in one of these parts, so either in this front part or in the middle part or at the end. So let's distinguish these three cases, and we can distinguish these three cases by looking at the prefix u. Namely, if u has a length smaller than m, then we know that this middle part falls in this begin piece. If u has a length between m and 2m, we know that this middle part falls in this middle part here. And if the prefix u has a length larger than 2m, we know that the prefix falls in this last part. So the first case, the length of u being smaller than m, then we know that this v and y fall in this begin part of a's and b's here, but it does not fall into these a's or these b's. So if we pump 0 times, so we drop v and we drop y, we know that v and y contain at least one a or one b. Then it means that we remove a's from this first part, and we remove b's from the second part, but not from these latter two parts. So we have removed at least one a or one b from this first part. The last part stays the same, a to the m, b to the m. So this word that we get no longer can be a word of the form ww. It's no longer in the language. Likewise, if the length of u is between m and smaller than 2m, then if we pump 0 times, we now remove b's from this middle part or a's from the middle part, and we know that we have removed at least one b or one a from here. And again, if we remove at least one b or one a, but we leave the number of a's in the beginning and the number of b's in the end the same, then this word cannot be of the form ww anymore. So this word cannot be in the language L. And finally, if the length of u is at least 2m, then we have that this middle part falls in this last part, a to the m, b to the m. So if we pump 0 times, we drop v and y, we have removed at least one a or one b from this last part. And again, since the first part is left unchanged, this word cannot be of the form ww, so we are not in the language L. So we have derived a contradiction in each case. Thus, we may conclude that the language does not have the pumping property, and since it does not have the pumping property, it cannot be context-free.